Up at the top of the next page of your handout, you need to know that LRAM, RM, and MRAM approximations are sometimes referred to as Riemann sums after Mr. Riemann. We'll hear more about him tomorrow. And again, they're only very rarely going to be exactly equal to the actual area under the curve, but we use them to make an approximation when an exact value can't be found. So there's two kinds of errors you need to know about that could happen when you use a Riemann sum. So here's a picture we've seen before. Notice here the velocity curve, the function's been given. I've been trying to estimate the area under the velocity curve. The velocity happens to be increasing. And notice that every one of those left-hand rectangles is a little bit too short to actually make up the whole area under its part of the curve. So you need to know that when a function is increasing, a Riemann sum approximation of the area under that function is always going to be an underestimate. Similarly, if I use right-hand rectangles and my function is increasing, each rectangle is going to be a little too big. So if a function is increasing, a right-hand Riemann sum, a right-hand rectangle approximation is going to be too big. It'll be an overestimate. You can imagine now if we used a function that was decreasing, the left-hand rectangles will all be too big, so the left-hand approximation is an overestimate. If a function f is decreasing, then the Riemann sum approximation, the right Riemann sum approximation, is going to be an underestimate. So here's an example from your handout. I have a rocket that has a positive velocity. Again, I don't know the velocity function. All I know is certain particular values, but that's okay. That's perfect for making a Riemann approximation. So here I've been asked to use MRAM with 3 subintervals to estimate the distance that this rocket travels between time is 10 and time is 7. All right, so if time goes from 10 to 70, I don't need this time value here at 1. Whoops. There we go. I don't need that data. And I don't need this data here at 80. That's outside my time interval that I care about. So now I've been asked to take this 10 to 70 time interval and split it up into 3 rectangles. So I like to draw this in. That's 10 to 70, that's a difference of 60, which means each rectangle is going to cover 20 seconds. So my first rectangle is going to cover 10 to 30. My second rectangle is going to cover 30 to 50. And my third rectangle will cover 30 to 70. They will never ask you to split an interval into little pieces. So they ask you for a midpoint Riemann sum, and it doesn't work out with exactly the right number of intervals. You got to check your work because something went wrong. Okay, so I know for MRAM, I'm supposed to look at the function value. I'm supposed to pick the height of my rectangle by picking the height of the function at the midpoint of the interval. So my first rectangle covers from 10 to 30, which means I care about how tall the rectangle is when time is 20. My second rectangle covers from 30 to 50. Halfway between 30 and 50 is 40, so I care about the function height when time is 40. My last rectangle covers from 50 to 70. I care about the height of the rectangle when time is 44. So here's my midpoint Riemann sum. All right, so here's my Riemann sum. This is 20 is the width of the first rectangle times its height, which was 22, plus 20 is the width of the second rectangle times its height, which is 35, plus 20, which is the width of the third rectangle, times its height, which is 44, and that comes out to 220 feet, if I'm not mistaken. And notice the units, each one of those rectangles was 20 seconds times some number of feet per second. The seconds cancel out, so that's feet plus feet plus feet, gives me 2,020 feet. Here we go with part B. Now I've been asked to use RAM with 2 subintervals to estimate the distance the rocket travels over 20 seconds. So each rectangle is 10 seconds wide. The height of the first rectangle will be 14. That's from the right endpoint. The height of the second is 22. And I can figure this out. So my answer comes out to 360 feet, and I can answer their other question. 360 feet is an overestimate because V of t is increasing.